But the load drive requirements are not necessarily the drive requirements of the CS stage. Maybe we have, for some reason, to place impedances in series or in parallel with the signal path, and then the excursions of the CS stage in current or in voltage may be larger than the excursions at the load, because these impedances in parallel or in series with the signal path, they act like attenuators. And there can be energy storage in it, or there can be just, if they have a real part, losses in it. So let's look at the output stage drive options that we have, because now it turns out to be important that we need to drive the we need to drive the load with 50 ohm. So what are the ways to do that? How could we drive the load from 50 ohm? Generally, if you design the CS stage, the output impedance is not 50 ohm, so you would have to do something about it. So what options do we have there? So the first option will be, let's do no feedback at the output, not at all. So then all the properties should be there in the CS stage itself. The output impedance of the CS stage should then be 50 ohm. I'm not discussing whether this is difficult, yes or no at this point. I'm just making an inventory, what kind of drive situation we meet. So if so, the output stage just needs to drive 50 ohm. Because that's all what we have as an external load from the CS stage, and it means, again, like the sine wave is 320 millivolts peak, and with the noise we have 675, just as done on the previous presentation. Another way is to apply voltage feedback at the output, but only voltage feedback. Voltage feedback means we are measuring the voltage in the output, putting it in a feedback network and doing something, comparing it with something at the input, like current or voltage. And it means parallel feedback at the output. If you remember well from the bachelor classes, parallel feedback at the output with a high loop gain, so ideally would result in zero output impedance. But that's not what we want. We want to drive the load with 50 ohm. So having zero output impedance of our amplifier, we need to put 50 ohm in series with it. This is usually called brute force impedance matching. You just put the impedance there that you want to have. So the output impedance of the amplifier would approximate zero in this case if we have effective output voltage feedback, and we need to insert 50 ohm in series with the output to obtain a 50 ohm drive for the cable. So the output stage drives effectively 100 ohms, which is 2 times the voltage. It needs to have 2 times the voltage. So you see it is 320 millivolt it was, and it now 640 millivolt peak, which is more than what it's 1.28 volt peak to peak. And remember, we have 1.8 volt power supply. So if you do this and you have to deal with a Gaussian distribution of your input signal, then so it is like noise, then it was already 1.3 volt peak, which is 2.6 volt peak, and we have a showstopper because this doesn't fit in 1.8 volt unless, of course, we now go to another scenario, which is applying a transformer to bring down the output impedance seen by the load impedance seen by the amplifier. So it's not really a showstopper, but if we have to deal with this, then we probably would need to take measures in sense of making a matching network or a transformer. So it's not complete, it is not accurate, it's a rough estimate because we ignored current drawn by the feedback network. We are parallel sensing at the load. Remember, we are creating voltage feedback. So we are placing some kind of network in parallel with the load to sense the voltage. And if this is a resistive network, it requires current. And the current drive capability should be larger than 6.4 milliamps peak. I just ignored it for the moment and just show you that we have more on the table than it appears to be at the first place. So output current feedback, that's another option. Output current feedback means that we are going to sense the current delivered by the amplifier, put it in a feedback network, and compare it at the input, convert it to a voltage or a current, and compare it at the input with the input quantity. Output current feedback, if it is effective series feedback, it is generating an infinitely large output impedance. So in this case, the output impedance of the amplifier approximates infinity, which is also not that we want for driving the cable. We want to drive the cable with 50 ohm. But that's not a problem. If we have infinity, we can just place something in parallel with it to get 50 ohm, and that something, of course, is 50 ohm. So, but then the amplifier has to drive 50 ohm of the cable in parallel with this brute force impedance matching thing, resistor, which makes that we have to drive 25 ohm, which means 2 times the current. But still we have no voltage, no extra voltage to drive. We have 320 millivolts peak just for the sine wave, just as in the first case, but now we have the double current. For the noise, if it would have been a distribution like noise, so a Gaussian distribution, and we want to have no clipping for 97% of the values, then we need to process 675 millivolts and double the current, which is 27 milliamps. But of course, in this case, we are sensing the output current with the feedback. The load current or the output current, which means we need some sense element. And if this sense element is not a non-energic one, if it is not a transformer, but if it is, for example, a resistor, then there is an extra voltage drop across it and we need to drive more voltage. This is not yet taken account, just as in the same situation as I did with the output voltage feedback. You can imagine that the price for brute force is quite high. You see, we are just doubling the excursions and have, of course, a power efficiency that is dropped to 50% maximally. So isn't there a smarter way? Yes, if you have followed our bachelor course, then you know we can do both output voltage and current feedback to establish an accurately defined output impedance defined by negative feedback. So, and then ideally, we would obtain 50 ohm, but maybe because of not enough loop gain, it will deviate a little bit. For this moment, we will just calculate that we have 50 ohm, and there's no extra measures to be taken to drive the cable, because we have taken the most effective measures. So we need to drive 50 ohm, which is exactly what we started with. 320 millivolts peak, 6.4 milliamp peak for sine wave-like signals, and for noise-like signals, we have these other numbers that we already discussed. Of course, if we are sensing current and sensing voltage, we need feedback elements that sense current and sense voltage. And if those feedback elements or networks are passive, then there will be a voltage drop and a current flow through the network. So that is ignored because that would lead to an increase of these values of the current and the voltage drive values. And of course, we are not exactly making a CS stage that can only drive 675 millivolt or 320 millivolt. We always must have reserve. So we must have extra for, let's say, losses that will happen that we didn't know upfront, but the big picture is here. And unfortunately, no one has been looking at this picture in the exercises, but this is something that has to do with the architecture of the complete amplifier. How are we going to drive this 50 ohm? Do we do it with feedback, with dual loop feedback, with single loop feedback, or are we trying to design the output stage, the transistor, having 50 ohm output impedance?